Are we ready?
Start?
Yeah, so welcome back everyone. I'm honored to introduce our next speaker, David Kazhdan from Hebrew University, who will speak about endoscopic decomposition.
Okay, in this talk I present results of a work with Yasha on construction and endoscopic decomposition for a character of reducible, very cuspidal representation of reductive p-adic groups in terms of spectral action defined by Fark and Schulze. In the talk I formulate a conjecture on extending this construction to our case of arbitrary characters of arbitrary reducible representation of the group. The existence of the endoscopic decomposition on the space of odd invariant functions on reductive group is a great discovery on Langlands. In particular, it's central for the authors who work on automorphic force for classical group. The definition of endoscopic decomposition will take the first part of the talk. Let F be a local non-Archimedean group of characteristic 0. G is a reductive group, and its points, F points. All results in conjecture presented in the talk call for arbitrary reductive group, but to simplify notations, assume that the group is split, adjoint, and simply connected. On the other hand, examples are for classical group who don't satisfy this condition. You should believe that we can give a definition. In any case, it was a lot of definitions. I try to reduce it to minimum. In the plan, in the first part of the talk, I define endoscopic subspaces of the space of locally constant and odd invariant functions on the subset of strong irregular elements. In the second part, you provide the definition of endoscopic decomposition of subspace spanned by characters of reducible representation. In the third part, present our work with Yaakov, provide explicit decomposition for very cuspidal, character of very cuspidal representation in terms of spectral action. And then the last part, formulate a conjectural extension of our work. Basic notations. Element is strongly irregular if it centralizes a torus. GSR is a subset of strongly regular element which is open and dense. WG is the space of odd invariant, locally constant, complex valued functions. On this set, we say maximal torus is anisotropic if its points have points compact. Element anisotropic if its centralizer is an anisotropic torus. Sorry? What?
Al S and S R are the same?
The same. It's invariance.
Strong irregular is the same as regular semi-simple. This is the proof of SR equal to R.
No, actually not. Because you could have regular semi-simple element whose centralizer is disconnected. Strong irregular is additional condition that centralizes torus. Okay, you're right. Then it's the same. Okay. As we know from Chevalier, any algebraic odd invariant group on G is the preimage of algebraic group on the quotient. But not every function, complex valued function, is a preimage of function on the quotient. A function is stable if it's a preimage of function on the quotient, and the natural notion of subspace of stable function. In the case of PGLN, every function is stable, but it's not true in general. That's important definition.
WG should be compactly supported?
What?
WG should be compactly supported?
No. No, it's like character of representation. It's not invariant, so it cannot be compactly supported.
But it is a function, not a...
It's locally constant function. So, example, in the case of PGLN, every function is stable, but then it means any two elements which are conjugate over algebraic closure of a field are conjugate over a field. It's not true for SL2.
I think you skipped a slide. Can you please roll back to the...
Yeah, sorry, you're right. So, for regular semi-simple element, we consider the omega bar of gamma, the set of elements conjugate over algebraic closure, and the omega gamma in brackets, the quotient. It's a finite set. And for a function, we have natural notion of restriction of this set. We say that function is invariant, is a function on this finite set. This is an example of two elements in SL2 which are conjugate over algebraic closure or quadratic extension of F, but not conjugate over F. This is dual group. I don't give a definition. Write a list of examples. Now, let G hat be the complex dual group. For an element, we denote the centralizer in G, and the conjugate class, we denote the centralizer, conjugate class of centralizer with elements. Now, there is an important notion of rigid conjugate classes. A semi-simple conjugate class is rigid if the centralizer is semi-simple. Psi G is a set of rigid conjugate classes, and we have a natural notation, omega psi, the corresponding conjugate class, and H psi is a split dual group dual to the centralizer. It's called endoscopic group of G.
It's a little bit too fast, I was... Go back to the previous slide, I didn't have...
Yes. Please stop, maybe I go too fast. I'm always afraid to go too slow. Okay?
CS is a centralizer of a semi-simple
This is okay.
Now, just notation, this psi G is actually a subset of a larger finite set related to not rigid conjugate classes, which I wouldn't define. I pretend they're equal, so some of my statements are not literally correct, but too complicated to make correct. And the second important thing is endoscopic subgroups. The subgroups of G are not necessarily its subgroups. So example, the identity is always rigid, and in case of if your group is symplectic groups, p-symplectic group, a dual group is symplectic, and then there exists a rigid conjugate class whose centralizer is isomorphic to SL2 cross SL2, so it is semi-simple group. Now, Langlands had a great idea of the existence of endoscopic subspaces in our space W, which span W, and there exists a transfer map from stable functions on the endoscopic group HUJI into the corresponding piece of functions on G. So this kind of, this is essentially what we're talking about, endoscopic decomposition, is decomposition of a whole space of function W into endoscopic pieces which correspond to stable function on different groups. Now, going to a slightly technical definition, but let me do this. So let T be a maximal torus on G. T hat a dual torus. Since T is determinant over a field F, the Galois group acts on the dual torus, and T tilde is the group of connected components of the set of invariant elements. And for conjugacy classes, it will be also rigid conjugate class, we consider intersection of invariant elements with this class and consider its projection onto quotient by connected component. Yes. Sorry? Omega psi is conjugacy class. Psi is a set of rigid conjugacy classes. Omega psi is corresponding conjugacy class, corresponding to element psi. Psi numbers rigid conjugacy classes. Omega psi is the corresponding conjugacy class.
So the torus, the initial torus is anisotropic. You're saying that gamma fixed points is a finite group.
If torus is anisotropic, then it's finite group. Set of elements, finite group. I'll give an example in a second. Okay? Now the kind of complicated, okay, they say, yeah, I think I go wrong direction, that's fine. Now the definition. With any element, regular semi-simple element, associate finite abelian group, such that the corresponding set, you remember we take conjugate classes or algebraic closure, mod adjoint next to the group is finite set, and the set is a torsor or very explicit finite abelian group, which defined it, but you can skip it. What's important, the corresponding dual group is isomorphic essentially to intersection with torus if gamma is anisotropic. So this is a kind of basic number theory involved in it. Example. So, suppose G is SL2, E over F is quadratic extension, T is the torus, non-split torus corresponding to E. So the torus is just kernel of norm map from quadratic extension to field. In this case, the dual torus is isomorphic on C star as a torus. The group gamma acts non-trivially for the quotient, mapping, of course, the weighted non-trivially element to inverse. The set of invariant elements is plus minus 1. And the corresponding group, a gamma, is a quotient of multiplicative group by norms, which is Z mod to Z. Now, the notion of small Fourier transform. So, the set omega gamma is torsor over this finite abelian group. If we fix a point, we can identify this set with group. So for any function on omega gamma, we consider its Fourier transform, which is a function on the dual group. Of course, it depends on the choice of the point, but a different point just changes by multiplication by scalar. So we consider the function on the corresponding fixed point of a torus, in the case of gamma is anisotropic. And we define, for any function we deny for SH, it's support. Okay, as before. So definition. If definition is really precise, is gamma is anisotropic, but I don't want to go in details. So if you take gamma regular semi-simple, and you take some psi, then we define subset of functions on the corresponding set whose Fourier transform lies in the subset of a dual group we define. What is T tilde psi is again, consider an isotropic case.
Okay.
It's the intersection of fixed points with conjugacy class. Psi is a conjugate class in a dual group. You take fixed point of a torus, fixed point of a Galois group acting on a dual torus, you intersect it with conjugacy class.
Conjugacy class or stable class?
Sorry?
Conjugacy class
This is
or
over
stable
C.
class?
This is over C.
It's over C.
Or
A dual group is over C. The tilde sub gamma is fixed point of a, we take centralizer of gamma, it is a torus. You take a dual torus, on it you have an action of Galois group. You take fixed points of this section. If gamma is anisotropic, this is the tilde of gamma.
Should be everywhere in the second line.
Okay. Yeah. Yeah. T tilde gamma, yes. Okay.
then who is S?
What?
Who is S in the definition?
S is a support of a Fourier transform of H. Just look, here it is. For a function we denote S of H, Fourier transform, support of Fourier transform. Now there is an important claim that if gamma is anisotropic, we actually have direct sum decomposition. This is the kind of basis of endoscopic decomposition. T gamma is finite set, so the intersection of everything is fine.
No, but omega gamma is square,
It's finite set.
so it's just set of.
It's finite set. Okay? Definition. The definition is not absolutely correct, because as I say, it's correct for elliptic elements. Anisotropic elements should be slightly corrected, but I don't want to go to it. We define for any psi, we define W psi, subspace of functions whose restriction on every conjugacy class of algebraic closure lies in the corresponding subspace. So these subspaces span the whole space, but they define direct sum decomposition only if gamma is anisotropic. Now, if there were direct sum decomposition for all gamma, then we can apply this decomposition orbit by orbit, conjugate class by conjugacy class, to define the decomposition, or try to define decomposition of a space WG. But in absence of such decomposition, it's not clear how to construct decomposition, endoscopic decomposition of a space. Okay, this is the end of the first part.
Don't have the decomposition. Time doesn't know how to define it.
There is decomposition for important subspace, what I start now, but not for all functions.
So it's not known.
Not known. For GLN, PG, SLN I can explain, but in general it's not known.
In the end it will be.
No. Okay, for me not. Doesn't matter. It's, the second part of the talk, I would like the composition, the scopic decomposition of a subspace spanned by characters of reducible representation. This exists. This is the only thing which is needed.
So just recap one. So you on the elliptic part, but not on the whole thing.
We know a full game, if you take subspace generated by characters of reducible,
That will be.
this would be. Right now we know how to do an elliptic part, we don't know what to do outside. You take a character of square integral or cuspidal representation, you decompose it, a restriction on anisotropic elements, no problem. You don't know what to do afterwards. Not just, okay, now things which must have known, just go. You have H in algebra of locally constant, compactly supported measures on G. RG is a category of finite length representation. KG is category, a K group of this category, reducible representation, and we have notion of character of any representation, which everybody assume knows. The following result in Krishandra, and here we use the fact that our field is characteristic zero. First part is known for all field, is that restriction to regular set of dense, open dense set of regular semisimple elements is locally constant, so it belongs to now space. And the character, the important thing, non-trivial, that this function is locally L1, and therefore we can define functional on our space H. A character is given by this function. This theorem defines isomorphism between K-theory or our category subgroups by characters. And we can tensor with C, we consider subspace over our space WG, which we work with. Now, in the category of that LB a Levi subgroup, we know there exist functors of unitary parabolic induction in Jacquet functor. They define the corresponding, the analogous maps defined on characters. And you can consider subspace in all space generated by images under induction of, so to say, good functions from proper Levi subgroup. Now the trivial thing is that for any function, the subspace generate, of course, the center of Levi acts on the image over Jacquet functor, and a statement for any f under action of center, you get a finite dimensional space.
What's S?
S is subspace generated by the action of the center. Or you take function f, you apply Jacquet functor, you get function on Levi, and now you apply center. It will be finite dimensional space. Now I cheat. I provide something which I call a definition, but the fact that correct definition is a conjecture. I'll cheat. Now I provide a definition of subspace defined by Arfel. This was honest to work, which is complementary to induced part. This subspace can take characters of all square integral representation. But before I give a definition, I consider an example of SL2, which is integrative. So let G be SL2. Theta be set of non-trivial quadratic characters of F star. For any theta, pi theta is representation of SL2, unitary induced from a character. And the following is true. This representation is direct sum of two reducible representations. Let's consider difference between these two representations. Of course, it's defined only up to a side, but it doesn't matter for us. This space, the difference lies in the space I promised to define, and the whole space is spanned of these differences and character of square integral representation. This is kind of way how this subspace look. Now a definition. We say the character of a star is negative if some power of character is a very simple form, and Q minus valuation of A times some positive number. A finite dimensional representation is negative. All characters who appear in decomposition are negative. Let us have a parabolic subgroup. We say representation is negative. If our of a center is negative, if for any positive coroot, the composition is negative. And now we can define subspace. It's a subspace of function such for any properly V, the action of a center on a subspace generated by action of a center to apply it to Jacquet functor is negative. But as I say, this is repeat subspace generated by the action of a center. What? It doesn't matter. It's a rational number. If you multiply n by 5, you multiply n by 5. There exists n. So if for some L is rational number, then and that's a rational number. I say, I'm cheating. My cheating is exactly what you are saying. I said very clearly why I'm cheating. I'm sure it's true, but they don't know proof. It's fine. Yes. Okay. From there. Now let's take any field which is isomorphic to C. The definition which I gave of this defines isomorphism between categories of complex representations from complex and smooth e-representation, just the same. Isomorphism is created when a space inside the same. And since the definition of a space I gave didn't appeal to topology of C, the corresponding subspace could be defined over E, exactly the same, or doesn't depend on choice of beta, which is the same. Now, important theorem which I skipped is that this subspace, zero has to be Newton stress. This subspace is complementary to induced subspace. The whole space V is direct sum of what comes from induction and this Arthur space. Sorry? Come back? Okay, now proposition. This is Arthur theorem. I think uses some trace formula. I don't have any idea how to prove. The proposition is the following. Suppose we have function in V subspace. Then there exists unique set of functions of psi also in V subspace, such as F is sum of this function and function endoscopic. This is Arthur's result. Since the parabolic induction preserves the endoscopic decomposition, proposition, and we have direct sum decomposition, I have to say some words. Proposition defines endoscopic decomposition for any function with linear combination of characters. Unfortunately, proposition does not provide information of a space generated by these endoscopic components. Its very existence result, but very not implicit. Even in the case when F is a character of reducible cuspidal representation of G. The third part of our talk, I outline an explicit construction of the endoscopic decomposition of characters, of very cuspidal representation from our papers, Varshavsky. This construction is based on spectral action defined by Fark and Scholz, a remarkable paper, a geometrization of the local Langlands conjecture. So we fix isomorphic QL bar with C. So
this endoscopic decomposition on anisotropic elements.
Oh, well, no, not on the tropic elements. Let's go back. No. It's trivial. It's not. For any function is Arthur subspace, which I defined. For
The second part, I said the first part was anisotropic. The second
Yeah.
part was on the induced part.
No, it's not anisotropic. Arthur subspace is not. Character square integral representation belong to Arthur part. They define everywhere. He defined decomposition for characters of square integral representation everywhere, not only on isotropic elements. This is a theorem. Theorem is, if you take any function in this subspace, there is unique decomposition. The subspace defined everywhere. There exists unique decomposition, endoscopic decomposition. Okay?
On this part,
Arthur, let's call it Arthur's part. I wrote AR, saying Arthur. On these Arthur piles, there is decomposition. Now, the whole thing is direct sum of this part and induced. You actually can decompose it canonically, direct sum of induced from Arthur parts of Levy, and then apply decomposition.
so this furnishes the decomposition of the whole.
Yes. Yes.
Which is
Yes. Yes.
what's the structure? How the third part relates to that?
The third part produces, expresses this endoscopic decomposition in terms of spectral action.
So a different way to decompose.
What?
A different way to decompose.
No, it's the same way, but it is constructive way.
Different way to obtain the decomposition.
Yes.
Yes.
No, this
No.
compatible with decomposition into fact.
Okay. Okay. So we choose isomorphism. It's kind of a went already. And we define Weil group, which everybody knows, it's written here. A Langlands parameter is a conjugated class of continuous homomorphism of WF to G hat, where G hat is QL bar group. We consider it not as a complex group, but QL bar group. Langlands parameter is semi-simple. The closure of image is reductive. The risk closure is reductive. We denote as phi the centralizer. Semi-simple as elliptic is a group is finite, and F elliptic is a set of elliptic Langlands parameters. This is why I don't use elliptic for elements, because I use it for packets and I don't want to mix up. Now, for an elliptic Langlands parameter, we define by C phi, there are conjugated classes of these finite groups. For elliptic parameter, this centralizer is finite, and we consider set of conjugated classes. Now the claim is that conjugated class, which you can consider its corresponding conjugated class in the dual group, it always reaches it. So it means that for any C there exists psi C, we define this conjugated class. We identify the algebra of finite dimensional representation of this finite group with algebra of functions, most probably functions, not Z, maybe Q, but it doesn't matter, function on this conjugated classes. Just to every representation of associated character. It should be Z bar, not Z, but it's relevant here. And we denote by delta the characteristic function of conjugated class. Now come to Fargan-Scholz. Fargan-Scholz associated with an irreducible representation, semi-simple Langlands parameter, and the reducible representation is very cuspidal if parameter is elliptic. Now what is known is that very, very cuspidal representation is cuspidal, but there are many cuspidal representations which are not very cuspidal. So it's now, so we fix an elliptic Langlands parameter. We consider denoted by phi phi packets, which is set of all reducible representation with this parameter. And we can say the space theta phi spanned by characters of the representation. Now, the spectral action provides an action of the algebra of representations of this finite group on this finite dimensional space, and in particular, since we identify representations of S phi with functions on conjugate class, we have a map from functions on conjugate class to S phi on C phi into endomorphism of our space. Example. You don't have to see example, but Pasha asked me to give example. I give example. Yes. It's K-theory of a corresponding category. Yes.
Tells you that you can consider the category of.
Well, it will be in a second. I come to this in a second.
I'm not saying what.
You have an action of a category of perfect complexes okay, you know what? Wait for it. In 2 minutes we come to this. Will be some notations. It will be easier for me to talk. So in particular, if you consider extension of the Galois group Z2 cross Z2, and you consider homomorphism in the dual group with this image, then the corresponding centralizer is, the group is commutative in PG, so the centralizer equal to itself. The corresponding Fark-Schulz packet consists of 4 cuspidal representations. Now, the main theorem of our lecture is that the decomposition is given by a very simple formula. You take a function in this space, you apply characteristic function of a corresponding conjugate class, and you obtain endoscopic decomposition. It's kind of very simple statement. Now, in the last part, I formulate some conjecture. My kind of cheating was necessary. I was sleeping, but my cheating was important for this conjecture. But, so let X be the scheme of homomorphism of Val group to G. The group G hat acts by conjugation, and we have a quotient stack. So more or less by definition, Leibniz parameters occupy by points of this stack, and elliptic parameters divide an open substack is a motion the quotient stack of point by S phi. Bar is left over from previous.
It's just the same as S phi.
Yeah, it's S phi. Просто bar. Okay, now your question. Let A be the metric modular infinity category of perfect equal complexes on this stack. The spectral action provides an action of this category on the appropriate category of constructible complex of sheaves on the stack of G bundles of Fark-Fontaine curve. This is spectral action. Let K of CRG be the K group of this. So the K group of A of symmetric modular category is a structure of commutative algebra which acts on this K theory and therefore K theory tangent QA. Now, the space contains our space generated by characters as a subspace. And now we can formulate conjecture. Arthur has defined endoscopic decomposition, in particular, defined subspace generated by endoscopic components. The conjecture is that it is just image of this let's take F in the Arthur space. It means it's sitting over one point. It's important. If you take an Arthur space, then the space generated by the scoping component of F is just what generated by the action of algebra A. Our main theory implies the validity conjecture, validity, and more. Our result provides explicit cathodic decomposition and not only describe the space generated by this. But okay, I'll stop here.
Please go back to part 2.
End of part 2.
Part 2, where you define this decomposition.
Yeah.
Decomposition of the arc.
Up. I do.
This proposition.
Yes.
It's the previous one.
Yes.
No, what?
Yeah.
Yes, here.
The proposition.
Conjecture is relies on this proposition. We kind of.
Sorry.
So this conjecture relies on this proposition.
No.
No.
Conjecture provides endoscopic decomposition. Statement is that action provides endoscopic decomposition. The proposition uniquely determines what is endoscopic decomposition. The conjecture provides, you can do more. I just, in our paper with Yasha, we provide not only space, but we describe, it's exactly the same statement should work.
Back to the conjecture at the very end.
Yeah. Okay.
Where is A defined?
A is just here. A is a K theory of this symmetric monoidal category.
No, there was sub A sub F A sub X.
Sorry?
The conjecture says that A.
A of F. You just apply algebra to element. A acts on this space. Now, there is a statement here. Let me. A, algebra A, acts on K of C of G. My claim is, and I think this I can prove, that if a group is simply connected and your function lies in Arthur space, then now this K of C of G contains subspace generated by characters, just as it contains Arthur space. My claim the Arthur space is invariant on direction because it's elliptic. It cannot move anywhere else. It requires a proof. It's not absolute tautology, but I show it is true.
One more time, please do the next.
Next. A priori, right side lies in the bigger space, in K of CR. So this conjecture implies that it lies in the smaller subspace and equal to this.
Are there any more questions of Dennis or anybody else?
I have a question. So, I mean, you had some
If you can go a little louder.
So, you had some statement which I can. Question is sort of how do you prove it in the following sense somehow? What do you know about Varshavsky? I mean, Varshavsky is a kind of abstract
Okay.
So what kind of properties of the section do you?
Yes. There is a work of three authors, Jacopo, remember names, Harris and, okay, no, so,
Hansen, Kajeta, and Weizmann.
yeah, who computed the action of these representations of a group CF, how it acts on values of characters on elliptic set. This is not very.
Who acts?
You take spectral action. You take element of spectral action is function on conjugacy classes of the group S5. You apply, you start with some character. You apply, it doesn't matter which one. You apply S5. Now some function, you have some function from this space V spanned by characters. You apply your function on the final group, you obtain new function. They wrote explicit formula, not very difficult to prove. How express values of new function on elliptic elements in terms of original function on elliptic elements and the function on this final group. This is the input which we use. Absolutely right. Have to use something. We have to use something. This is the input which you use.
And so that is a black box.
I use everything as a black box. That's right. Yes, of course.
Last question. Elliptic Galois parameter?
Elliptic Langlands.
Langlands.
They're just to be.
And let's look at the. So we can look at the. The Varshavsky category.
The corresponding packet.
Yes, and let's intersect it with representations of Varshavsky category has representations of group G and other stuff.
Yes.
So, in particular, the graphic ring of the centralizer acts on the graphic group of this
Intersection.
from this intersection. The idea is that you're saying that the corresponding decomposition into eigenspaces endoscopic.
Yes. Yes. That's the statement. Okay.
Okay, thank you very much.